Welcome to Chapter 4, where we dive deeply into graph theory's role in software testing. Graph theory offers powerful tools for testers to visualize complex dependencies, track test coverage, and optimize test strategies. We begin by exploring directed graphs and edge weights. In a directed graph, each connection or edge has a specific direction, which is crucial for mapping workflows or processes where sequence matters. This structure helps testers visualize user flows or data processes that follow a particular order. Edge weights add a layer of depth, assigning values to each edge to represent factors like time, cost, or risk, which allows testers to prioritize paths that might be more critical or require focused testing. Next, we focus on graph traversal techniques, essential for navigating the nodes, or points, in a graph. We use depth-first search, DFS, for deep exploration along one path before backtracking, which is useful for detecting cycles, verifying dependencies, or identifying recursion points in software flows. Breadth-first search, BFS, on the other hand, explores nodes layer by layer and is ideal for finding the shortest path or ensuring that all nodes are reachable, helping testers ensure full coverage in complex systems. We then move on to dependency graphs, a powerful way to map out component dependencies within software systems. These graphs help testers identify crucial connections, locate potential bottlenecks, and prioritize which components to test first based on dependency chains. For example, if a function is highly dependent on multiple other components, testing its dependencies first ensures stability and reduces test redundancy. Another important technique is subgraph testing, which involves isolating specific sections or subgraphs within a larger graph to test independently. This approach is particularly useful for modular testing or testing individual subsystems without needing to run the entire application. By focusing on isolated subgraphs, testers can more effectively identify issues in distinct sections before integrating them into the main system. State transition testing is another valuable application. This technique models a system's states as nodes, with edges representing transitions between states. This approach is particularly valuable for testing interactive or responsive applications, where the system behavior depends on user actions or specific inputs. State transition testing allows testers to verify how the system responds to each input and detect any unintended states, ensuring robust system behavior under varied conditions. Finally, we address cycle detection. Cycles occur when a path in a graph leads back to an earlier node. Detecting cycles is critical to prevent infinite loops or repeated actions in software. For example, if a user flow unexpectedly loops back to the start, testers can use cycle detection to pinpoint the issue, ensuring that the system behaves as expected without unintended repetitions.